Okay, now we continue with subchapter 1.4, which is on-off control system, proportional, integral, and derivative control mode. So basically, we have two types of controller, which is discontinuous controllers and continuous controllers. Okay, later on I will explain in detail what is discontinuous, what is continuous. Okay, single loop control system. The action of controllers can be divided into groups based upon their control mechanism function. Each type of controller has advantages or disadvantages and has different application. Okay, like what I'm saying before, we have two types of controllers, which is discontinuous controllers and also continuous controllers. Okay, for discontinuous controllers, the example is on-off controller. Meanwhile, continuous controllers, we have P, PI, PD, PID controller. So P for proportional, meanwhile I for integral, D for derivative. Okay, next we move to what is discontinuous controller mode or on-off controller. Okay, basically there is a two position mode of control in this on-off controller, which is on or off. Okay, the controller output is a digital representation of single binary digits, whether whether 0 or 1. Okay, so normally 0 is stand for off signal, 1 is stand for on signal. So this type of controller is simple and inexpensive. Type of control action in which the manipulated variable is quickly changed to maximum or minimum value, depending whether the controller variable is greater or less than set point. So this on-off controller will send the information to the final element, which is valve, motor, or etc., whether to open the valve if it want to switch on the flow or something, to close the valve. So basically in a real situation, a valve opening can be varies from 1% to 100%. So for the on-off controller, they will not open in a percentage manner. That means they will not open like 50% opening, 70% opening. It will push to maximums. So if the controller send information to on the system, so that means the valve will start to open 100%, and if the controller send the information to off, and then the valve will close 100%. Okay, normally this on-off controller will use in a slow process response. Okay, the example is temperature. Okay, two level in on-off control. So like what I'm saying in this statement, whether the valve will be open or closed. So that show how the discontinuous manner phenomenon. In other words, it is discrete. So it will not open by percentage. It will whether open or close. So if let's say we use motor as a final element, it have a forward or reverse. Okay, so this is the block diagram of an ideal on-off controller. So same like feedback control in a previous video, we have set point as per our input. It will send a signal to the comparator, and the comparator will also receive signal from the sensor. We also have a sensor. The sensor will measure the control variable and also process variable, and it will send the error. This comparator will come up with the error. Error will send to the on-off controller here. So this on-off controller will decide whether to open or close the final control element in order to adjust the manipulated variable. Okay, this is the graphical response for on-off controller. So if in the case the control variable is greater than set point, so it means this control variable is already exceeded, right? So when it exceeded the set point, the system will be the controller will ask the final element to shut off. Okay, this one represent the shut off of the final control element, and then the system will the response will start to increase and go down, and then if they reach the set point, if they reach a set point, the system will go down, and then if the control variable start to become less than set point, the system will start to switch on back. So this shows the discontinuous manners of this on off, switch off, switch on, switch off, switch on. So if let's say continuous manners, it will continuous from 0, increasing, decreasing, and so on. Okay, so this is the application of the on-off controller, which is heating system. So if the temperature in a room rises above the set point, the heater will turn off so that the room temperature will go down and reaches its set point. If the temperature falls below set point, the heater is turned on in order to increase the temperature, achieving its set point. So the instantaneous change in control action due to the small error cause excessive wear of electrical contact and moving part of final control element. This means that this is the disadvantage of this on-off control system, because if there is any changes, we need to adjust the final control element, sudden open and sudden close. So that's why it can cause excessive wear of electrical contact and also moving part. Okay, so this is the example of thermostat. Thermostat is used. Thermostat is a simple negative feedback control. When the temperature measured, known as a MV, goes below set point, the heater will start to switch on. And another example could be pressure switch on an air compressor. When the pressure drop below the threshold, which is set point, the pump is powered in order to increase the pressure in an air compressor. Okay, the advantages for this on-off control is cheap, robust, efficient. The disadvantage is the controller output bears no relationship to the error signal. So other application example is kettle, water heater, air conditioning system, and also iron. So like what we experience with air conditioning system, if we feel if in that room have a air conditioning system, if we feel too hot, we will increase the temperature, right? If we feel too cold, we will increase the temperature. If the temperature in the room is hot, we will decrease the temperature. So that was on-off controllers working principle. It don't have any automated working principle that can detect, okay, hot already, the system need automatically decide how to do. So in on-off controller, we don't have such thing, but in a continuous controller, yes. Okay, now we move to continuous controller mode. Okay, basically we have PID controller inside this continuous controller mode. So for the continuous controller mode, controllers which automatically compare the value of control variable with a set point to determine if an error exists. So those controller will cater the error signal given by the comparator and make a corrective action based on the error itself. Next, it adjusts its output if error occur according to the tuning parameter that have been set. So the output will be adjusted based on the error according to the tuning parameter. This tuning parameter is a setting that we input into the controller. So it seems like you want to hear the radio, right? You want to switch the channel, right? So you need to tune to some numbers, so some frequencies, so that you can hear the value in a stable, and you can clearly hear the sound from the channel itself, right? So actually this tuning is same. We need to tune the setting of the controller itself, and we have a few settings like P, I and D. So it's depend on what we want. If we want that system to be stable, and then we can use each one of these controller. Each of these controller have different working principle. Okay, let's have a look in detail this type of controller. Okay, so for the proportional mode, the function is to decide how much correction should be made. So it scatter the magnitude of the correction. Okay, so for example, we have a level system. Okay, if we don't install any controller for this level, in other words, is open loop control system, the level will keep increasing until we shut off the system, right? So if we install the controller, if let's say we want set point around 7 meter here, so this proportional modes, the function is to do a correction. How much correction? It will decide how much correction should be made. If let's say this level go beyond the set point, exceed the set point, and then it will calculate how much correction should be made in order to make sure the control variable, this level, achieve the set point. And by the decision they made, we can get this type of response, nearly achieving the set point. In some cases, in some process, this proportional mode is unable to bring this control variable to the set point, which is 7 meter. Maybe it has slightly error around 1 meter, maybe 6 meter only. Okay, in order to cater this error, we need to add in integral mode. The function of integral mode is to decide how long the correction should be applied. So the main characteristic of this integral mode is the duration of adjustment to the controller output. So normally, if we add in integral mode into the proportional mode, this kind of response, this is P controller only, we will get this integral mode also have ability to eliminate the error obtained inside this P controller. So it will bring the control variable near to the set point here. Okay, lastly is how derivative mode. The function is to decide how fast should the correction be applied. Okay. Okay, this one is PI and we have another response PID. So normally in the PI, in a dynamic system, we will get a bit overshoot here, and then after certain time they will reach the set point and constant. Okay, this derivative mode, the function is to fasten. Okay, maybe we can say it here. In order for the level to reach a constant steady state around 30 minutes. So by using the derivative mode, we can fasten the response to reach set point, fasten the control variable to reach set point, maybe around 10 minutes. Basically for level, actually it's only took around less than 5 minutes actually to reach set point. So this is just the example. Okay. So the other advantage of this derivative mode, it can eliminate this kind of overshoot and cause the system to be stable and reach set point faster as compared to the integral plus proportional mode. So this one is if we add up D to the PID to PI. Okay, for your information, this kind of controller will be used depending on the system itself. Okay, let's move to this. Okay, sometimes the process is highly dynamic, so we need to use both all those three type of controller in order to cater the fluctuation or the changes occur in the system. But if let's say if you use proportional and then you already got the response like this, like PID, and then it is sufficient enough for you to use P only. But if you use P, your control variable is not achieve your set point, and then you have to add up integral. Then if you add up integral or and then you get this kind of response already, and then you don't need to proceed with derivative, because this kind of response is stable enough and is a good response or robust response already. But if your system is highly dynamic and then you still have this kind of overshoot and your time is about your steady state is not being reached, and then you need to add up the derivative controller. Okay, basically this is the same block diagram as mentioned in the previous slides. You have a process. From the process, we have a process variable or control variable. So this control variable will be measured using sensor, and then it will be sent to the set point, and then set point it will send to the comparator. It will be compare with set point and control variable, and then this information is sent to the controller. So this controller setting P, I or D is depend on you. You can tune it by try and error method or by available tuning methods in order to get the good response in here like this. And then this controller will send information to final control element, and then it will adjust the manipulated variable. Okay, I think that's all for me. I hope you can understand. If you have any question, you can PM me or directly ask inside the group. Thank you.